Back to language development with Stefan. Today we're talking about arrow pushing. Arrow pushing is a way for us to kind of bookkeep to get ourselves from one resonance structure to another resonance structure. So here we go. Here is a system where I have an allylic anion. So you're looking at this, you notice the pattern that I just talked about in the last part of the video, the pattern of a pi bond next to a lone pair. Okay, cool. So how can I kind of use this to get to what that other resonance structure is? So the language that organic chemists use is arrow pushing. So arrows denote electron movement. This is not a great definition of that because here electrons aren't kind of like swishing back and forth, but they are kind of moving on the page. So here we go. Arrows always start at the electrons. You can draw it from that lone pair or the charge, and end where they're going. Here, my arrow ends in the middle of the bond, right? Not the end of it, not somewhere in space, but single-headed arrow starting from the lone pair or the charge, ending at the middle of the bond. So that basically means that I'm making a new pi bond there. However, can I just make a pi bond there? Well, no, right? There's already 4 bonds of that carbon. There's a hydrogen there that I guess I didn't draw because I don't need to. But I can't just do that. And so if these electrons are getting pushed in, then these electrons are going to end up on the atom. So notice that this arrow is kind of the reverse of this arrow. This arrow goes from the atom to the bond. This arrow starts at the middle of the bond and ends at the atom. So again, you can kind of think of this as electrons flowing from right to left, as I see it. But in reality, we're just describing 2 different things. It's not like electrons are going floosh, 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 floosh. This is our new resonance structure. Notice that here there's now a pi bond where we made a pi bond here. And here that pi bond is now a single bond and the lone pair. Nothing else changed. The only thing we need to focus on is this 3-atom chunk. Right? When we're doing resonance, we're often not engaging with the rest of the molecule, just that chunk where it's important. But I want you to get comfortable with that pattern. Lone pair, pi bond. Lone pair, pi bond. Right? Get your hand used to drawing that in order to go back and forth between resonance structures. In some ways, the allyl cation is a little bit simpler because there are only 2 electrons. And here, I think about this system as a door. Here are the hinges to the door, and the door is swinging. So these 2 pi electrons see this positively charged thing, and they're going to go over and help it out. So electrons are flowing from here to there. My new resonance structure now has a double bond here. Again, the arrow ends at the middle of that bond. And because I pulled electrons away from this carbon, I have a positive charge there. Right? As a tip, when you're drawing resonance structures, they really need to have the same overall charge. Right? If you have a cation here, but this is neutral, you did it wrong. You messed up. It doesn't mean you're a bad person, but it doesn't mean you're a good person, right? It just means you're a person living in the world, doing what they can, having adventures, you know, just kind of doing it. Anyways, the point here is that check your charges, right? If your overall charge is not the same, then something went wrong. But this is how we go back and forth with the allyl cation. It's only 1 arrow, essentially 1 arrow per 2 electrons. So this was a 4-electron unit, so 4 electrons, 2 arrows. Here I have 2 electrons, 1 arrow. And because I'm pulling electrons away from this carbon, I get this. Let's try one more of these. Acetamide. Here we go. So this has, again, that amide functionality. NCO, all right here. Really, really important in biochemistry and protein structure. But our pattern here is lone pair next to pi bond. So when I start my arrow pushing, I start where the electrons are. They are at this lone pair. So my arrow starts there, goes to the middle of that CN bond. Seems like it wants to make a CN double bond. That would give that carbon a fifth bond. Can't do that. Don't feel good about it. So this pi bond then has to go up onto that oxygen. Again, 3-atom chunk. That's the pattern. So now, I guess, double bond between the C and the N. Single bond to oxygen. Had 2 lone pairs, now has 3. Right? So here I had 2 lone pairs and 1 lone pair. Now I have 3 lone pairs and no lone pairs. But I also have charges that I need to deal with. This nitrogen is giving up electrons. It now has 4 bonds. That's a positive nitrogen. This oxygen is getting electrons. Extra lone pair, that's negative. So this helps explain why amides are so polar. They're so polar because of this really important resonance between that lone pair and that CO pi bond. Finally, one more. So here's a system where I've got 2 pi bonds in a chain with this CO pi bond here. So 3 pi bonds in a row. Again, I can think about pulling all the way up to that oxygen. So my electrons are going to start here and end up there. So here I go with my arrows. I start in the middle of the bond, draw it to the middle of the next bond. That would make a 5th bond here. So this pi bond goes there. Notice how my arrows my arrows seem to be all going in the same flow, like a waterfall or a beautiful cascade. That's kind of how this goes. And this last arrow then goes up to oxygen. Okay, so now, because electrons came from this carbon, right? This carbon only had 1 more bond. There's now 3 bonded carbon. That's a positive charge. And up here, this oxygen now carries a negative charge because it got electrons from that flow. Overall charges are the same. If I were to count hydrogens, my hydrogen count would be the same. Not only would it be the same, but no hydrogens would have moved. And that's one point to say, what's a mistake a lot of people make with this? A mistake people make with this would be to draw this whole thing and try to put that negative or that double bond here. That won't work because there are 3 hydrogens on this end because that's what that carbon is. And so I can't move any of those hydrogens away, nor can I give that carbon a pi bond without giving it a 5th bond, right? So again, what I like about trying to figure out resonance structures is that there's a really good, easy, and always correct way to check your work. Check your work by looking at the overall charge and by looking at all the atoms to make sure they're not moving, and particularly looking at the hydrogens to make sure that they're not moving, right? So that might mean doing what I just did here and actually drawing in all the hydrogens just to convince yourself that nothing moved. I recommend doing that, especially if you're new to this. Draw in your hydrogens to make absolutely sure that you did not accidentally move one, because it's really easy to do. This is imidazole. Imidazole is a really commonly used reagent in biochemistry. One of the amino acids that makes up proteins has an imidazole unit in it. Imidazole has 2 nitrogens, and each of those nitrogens has a lone pair. The lone pairs are pretty different. So where is their resonance here? So you can imagine that I have a lone pair next to a pi bond here. So if I draw that, again, arrow, it would go like this: lone pair to bond, bond to atom. And I can think about drawing a resonance structure of imidazole. Notice it still has the NH there, and notice that This is overall neutral. This has a positive and a negative charge, but it's also overall neutral. You might ask, can I think about resonance for this lone pair on this southeastern nitrogen, right? Again, just pattern-wise, I have the lone pair next to a pi bond, 3-atom chunk, just like Stefan said. And I can imagine drawing arrows to get to something like this. This lone pair is actually in the plane of the molecule. It is not part of the pi system. How can I tell that? Well, that nitrogen already has a pi bond. That nitrogen already has its p orbital filled with some electron. Here's a bad drawing, but the drawing that emphasizes that C-N pi bond. Here we go, right? So that pi bond is filled. Those are filled p orbitals. That lone pair cannot be in that p orbital because that p orbital is already filled. So that lone pair then is kind of coming out in the plane of the board, just like these CHs, right? So just like these CHs are flat and not in the pi network, that lone pair is flat and sticking out of the molecule, right? So that doesn't overlap. Generally, a general result, when I have a lone pair on an atom that already has a pi bond, this cannot show any resonance. Just to describe what I'm talking about with these orbitals. So I've calculated the orbitals of imidazole, and here you can see one of the molecular orbitals with the p orbitals, the pi bond. So here's the CN pi bond, and it kind of overlaps with the pi p orbital across the way. So as you can see, there is my CN pi bond. Here is the other combination of p orbitals that shows up. But then check this out. This is the lone pair from that nitrogen with double bond. Notice how the lone pair orbital is sticking out of the molecule. It's not in the plane like these are. It is sticking out. So the lone pair does not overlap that pi system. So the point here is that resonance is going to be really, really important for us to understand how these molecules function in the world. In particular, for imidazole, this tells us that this nitrogen is going to be a little bit of a positive charge because of this electron flow. Later on, we'll learn that this makes it a little bit acidic. It's willing to give up this hydrogen as an H+, right? But we don't see that kind of electron flow coming from nitrogen. We see that lone pair is stuck. That lone pair cannot go around the ring because it is not part of the pi system. So learning these rules is important. 3-atom system like this, good. Lone pair on a pi bond, no resonance.